About time to start, but I wanted to remind everybody you do have a online test that's due tonight at 11:59 p.m. Remember the online test, you're allowed multiple attempts, usually like three, and only your highest counts. You also have a practice test that's going to disappear tonight at 11:59 p.m. So make sure you don't forget to hit those and do that. Additionally, if anybody missed one of the old one of the old one of the former online tests, online test one or online test two, for instance, you need to email me and let me know that you missed it so that I can give you a chance to take it. You are going to lose some points because you were supposed to have it done on time. So just make sure you get it done. If you actually send me an old one, I'll probably make it due by Sunday of this weekend. Remember, next week we actually have spring break, so no one needs to attend next week. But I basically have put some of the labs and stuff that would otherwise be due next week. I've put them off to the following week. If and that's the way it all should be. So if you see any assignments that are due over the spring break, obviously they're not due over the spring break. They're going to be put till after the spring break. So that includes the homework on any chapters we haven't finished. We're in chapter 24. I suspect we will not, or excuse me, we're in chapter 7. I suspect we will not necessarily finish chapter 7 tonight, but we might. Okay, so if we don't finish chapter 7, then that means that homework that would have otherwise be done due this coming Sunday, it's actually going to be, if we do finish it, due the following Sunday. And if we don't finish it, it'll be due not the following Sunday, but probably at least Wednesday night of not next week, but the week after. So, anyways, I just wanted to get that out so everybody knew. So make sure you send me a text message or email if you need to take one of the old online tests, online test one or online test two. Make sure you get your online test three done tonight. And we're going to go ahead and get started. Does anybody have any questions before we get started? All right. So, first off, I want to remind everybody, go ahead and chat me your first and last name. So I'll have that as roll. I am going to go ahead and share my iPad screen with you guys. So let me do that. As I said, we're starting chapter 7. I had given you some ideas of things to think about with regards to work because I want you to, in general, in physics, period, the beauty of physics is it's mostly about things that you've interacted with or you have the potential to interact with. Like throwing balls is a projectile motion problem. Uh, Friction occurs in everyday life, a little bit of all that stuff. So it's really important that you guys relate the physics that we learn to actually everyday life. Unlike chemistry, where you can't necessarily see the individual atoms combining and making solutions, and most people don't have a number of chemicals they can mix together on a regular basis. So they have the disadvantage of sometimes they can't make things relate as well as us physicists do with regards to during lecture. So by all means, whenever you run into things, try to think how it's similar to something else. And for instance, in this case, we were talking about how work should be somewhat related to work that you know of in everyday life. So I mentioned that it seemed reasonable that the work done is proportional to the distance traveled. I made the argument that if you had, for instance, a 1 acre lot, then that 1 acre lot might be, let's say, 120 feet wide. And if I remember correctly, if you multiply 120 by 363, you get pretty close to 43,560, which is the number of square feet in an acre. So that would be a 1 acre yard if it's 120 by 363. If you're using a 2 foot wide lawnmower blade, then you can walk one swath parallel to the 363 foot dimension, and that'll cut out 2 feet. So instead of it being 120 feet wide, you've cut it down to 118. Then you go back the other direction, and that'll bring it down to 216. I mean 116. And then if you go again, that'll bring it down to 212, or excuse me, 214, 114, and so on and so forth. So when you're actually done actually cutting the whole acre, you're going to have basically 60 swaths back and forth times 363 feet each time. So you could basically say that whatever 60 times 363 is, that's the total distance you traveled, and that's the total distance over which you had to apply a force to a lawnmower. And it seems reasonable that we say work is proportional to that distance. And with that in mind, that tells us work should be proportional to distance. Now, additionally, if we were, for instance, to say it's going to be 2 acres, then we might have to do 240 feet by 363, in which case that would take, instead of 60 trips, you'd have to take a whole 120 trips, but each of those 120 trips would be 363 feet long. So you'd multiply 120 times 363. That would clearly be twice as far, and therefore you'd expect 2 acre lawn mowing would be twice as much work as 1 acre lawn mowing. And that's consistent with what I wrote here, which is work is directly proportional to distance. And I'm sorry I wrote it that way, but work is proportional to distance. Now, again, as I mentioned before, if we were actually doing that mowing with a 50-pound lawnmower, obviously you're not picking up the lawnmower. So 50 pounds isn't necessarily the force you'd have to apply to push the lawnmower, but 50 pounds is the weight of the lawnmower. And if it's on level ground, then you know the normal force should also be 50 pounds, right? That means the friction force, which is proportional to the normal force, is proportional to the 50 pounds. So if you considered a 1 acre lot cutting it two different ways, one case would be a 50-pound lawnmower, the other case would be a 100-pound lawnmower. I suspect you would also agree that the using the 100-pound lawnmower would be about twice as much work as using the 50-pound lawnmower. And from that, we're able to reach the conclusion that work is also proportional to force. Now, proportional just means thumbs up, thumbs up. That means if distance goes up, then work goes up. If force goes up, then work goes up. Okay. But it could be that it's proportional to distance squared, or distance to the 1/2 power, or distance to the 1/3 power. Any positive power basically would work. It could be distance cubed or whatever. Similarly, the same thing for friction, I mean, for force. But what I'll tell you is that what we've decided on for the units of work and for work itself is really work is proportional to F times D. So we then reach the conclusion that work is proportional to force times distance. And there's another thing we can take into consideration. If, for instance, I am pushing a lawnmower like an adult does, when you're pushing a lawnmower, the handle doesn't come up quite to your height of your chest. It's maybe somewhere between your belly button and your pecs or whatever. And you can just walk like this. Well, when you're walking like that, your arm is down at this angle. That means you have a component of force downward and a component of force horizontal. Well, it doesn't seem reasonable to count the force that's vertical, because that force isn't doing anything to make it move forward or backwards. So that component of force is a bare minimum, is just wasted. But in addition to that, since it's a downward force, we know that's going to ultimately increase the normal force, and that's going to actually make it harder because it's going to increase the friction force. So we really want not we don't want the work to be proportional to the total force necessarily. We want work to be proportional to the force that happens to be parallel to the distance traveled. So an update to this would be work is directly proportional to the component of force that's parallel to the distance. Or you could alternatively say it's the distance that has the component of distance that's parallel to the force would also be a way you could calculate it. So it just happens that vector analysis has created just such a quantity to help us pick out exactly what component of force we want. In fact, there's two vector algebra tools that you can use to pick out one, the component parallel to another vector, so a component of one vector parallel to another, and then the other quantity will pick out the component of one vector perpendicular to the other. Those two things are called the dot product, which is also called a scalar product. And that one's the one that picks out things parallel to each other. So what we're looking at it is sort of like an operation where you put in two vectors and out pops a number that represents the part of one vector that's parallel to the other vector. That's the dot product. Then there's another machine object thingy that we can use. And in that case, you have two vectors that you put in, and it spits out the component of the vector that's perpendicular to the other vector. That one's the what we call the vector product, or also called the cross product. We're not yet ready to go into the cross product, but I will show you what the dot product is. So to take that into account, we can say at least if the force and the direction of the force doesn't change at any point on the distance that we're traveling. So, for instance, when we were walking the 363 feet for one swath of the lawnmower, as long as that force that you're applying is a constant, then there's no need to use a formula any more complex than the one I'm getting ready to give you. And that formula is going to be work equals force times displacement. Okay. This is for a force that does not change over the displacement. And remember, that's the displacement we learned about in kinematics. So if the force, meaning the magnitude and direction, doesn't change anywhere along the whole distance vector d that you apply the force along, then you could just use this formula: work equals force. Notice I have a vector symbol over it. Dot. Notice I drew a dot, and then d with a vector symbol over it. That is called a dot product, and we define the dot product as follows: A dot B is equal to, now the magnitude of an A vector, we can either write that by writing the A vector with a little arrow over top of it and then put absolute value bars on it. Some mathematicians in some math classes will put double vertical bars on each side. So 1, 2, and then 1, 2 over here. That's also another indicator of the magnitude of a vector. But an easiest way to do it is just write the vector symbol A without the arrow over it, and that's understood to be the magnitude. So A dot B has a magnitude, and it is just a scalar quantity. So when I say it's the magnitude, that's the whole thing. There's no vectors that come out of a dot product. But A dot B is going to be the magnitude of A times the magnitude of B times the cosine of the angle between them. And for that to make any sense, you also have to have a diagram to represent it. So let's call this vector A. Let's call this vector B. And since they're tail to tail, we can then call that angle theta. Notice it's the small angle, though. It's not the big one that goes from A counterclockwise all the way around to B. It's just that smallest angle. So that is actually what we call the dot product. You take the magnitude of A times the magnitude of B and multiply it by the cosine of the angle between them. Now, I'm going to say A dot B is equal to the dot product. It's equal to the dot product, but it's also equal to what we call the scalar product. So what I'm telling you is the dot product takes two vectors in and spits out a scalar. Okay. Now, to make some sense of why I told you A dot B is a mechanism that allows us to pull out a part of A that's parallel to B, or alternatively, a part of B that's parallel to A, that's what the dot product's one of the reasons it was created. So I'm going to show you why that's the case. If we imagine breaking up the vector A into two parts, a component that is perpendicular to B, that's A perp, and then a component that is parallel to B, and that's going to be called A parallel parallel. And since I've drawn them as actual vectors, it's probably best that I go ahead and uh, put a little symbol over it to represent it as a vector. Now, if you look at that, you can see that if I take the cosine of theta, which equals adjacent over hypotenuse, the adjacent is A parallel and the hypotenuse is the A itself. And we really only talk about the ratio of the magnitude, so I don't have to put the vector symbols here. But the key thing is to understand that the component of A parallel to B is actually equal to A cosine theta. So you can see that this part multiply, well, let me do it with a red symbol. This part A multiplied by this part cosine theta gives you the component of A that is perpendicular to B. Or excuse me, that is parallel to B. So that's one of the reasons. Now, if we also considered the other way around, we might say, wait a second, I can break B up into a component that is perpendicular to B. So this one would be B perpendicular and a component that's parallel to A, that would be B parallel. And of course, that's a vector as well. Now, looking at that triangle that we have made out of the two green legs and the blue hypotenuse, you can see that in that case, cosine theta is equal to adjacent over hypotenuse. And that, of course, is B parallel over B. Therefore, B parallel is equal to B cosine theta. So now we have that B and cosine theta gives us B parallel to A. Just like the A cosine theta gave us A parallel to B. Okay, so that's the importance of this dot product. We can see that, in fact, it does take and give us the component of A parallel to B, but it's also times the magnitude of B. So if you don't want that magnitude of B, which in this case we do, because we want the magnitude of the distance that the work is doing. In other words, when we push the lawnmower, we're applying a force over a distance. That's the idea of what work is. And when we do that, then you have to take the component of the force that's parallel to the displacement vector d, and then you got to multiply that by the whole length d that you go. So you see that AB cosine theta gives us exactly what we want, and that's why we define the work to be F dot D. Now, in order to make use of that, we still need to understand exactly how to calculate A dot B. So before I go to the next step, which is generalizing work to include a force that actually varies along the path, because in principle, you're walking that lawnmower the 363 feet and you're applying that force at each of that distance. As long as that force and both magnitude and direction of that force doesn't change, we can just use that F dot D and it gives us exactly the right answer. That's great. But if you have the F changing, then you're going to have to divide the path up into little segments. And the little segments have to be small enough that the force, neither direction nor magnitude, changes over that small segment of the path. And then you do F dot D for that little itty bitty path, which instead of D, you might call that DL or something like that, meaning a differential length. And then you do F dot DL. And then you go to the next length and you do a new F, that'd be like F2.dl2. And then the next one would be F3.dl3. And the next one would be F4.dl4, and so on and so forth. But in doing that, that would require you to think, okay, is this length of the line segment that we're walking along, is that really small enough? In doing that, you'd have to sort of iteratively look at the segment, see if the force is small, see if it's small enough that the force doesn't change appreciably for the precision that you're using. So, for instance, if you're doing two decimal places, there's one length of the path that's small enough. But if you're doing three decimal places, you might have to make the path even smaller. And if you're doing four decimal places, you might even have to make the path smaller still. That being said, one way you can definitively make sure it always works is you can divide it up into a bunch of little segments along that path. and then take the limit as the length of those segments approaches zero, and then add up all those terms. Again, F1 dotted with D1 plus F or DL1 and plus F2 dotted with DL2 plus F3 dotted with DL3, and do that for, in fact, since you're taking the limit as the length goes to zero, it's going to take an infinity of little sections to do it. Therefore, we're going to actually perform a Riemann sum of those little dot products. So that's where we're going to generalize. We're going to take the next step, and whenever the force can vary along the path that you're doing, you're going to have to integrate that. And that is not just strictly speaking an integral like everyday life. It's actually what we call a path or a line integral, which you can find in the usually in the last chapter or two of your calculus book. Okay. I've never known of any class to get to that, but I did have a student tell me last night that his Calc 3 class did cover the line integral or path integral. So, anyways, it does exist. Now, with that in mind, I need to go a little further to teach you something about dot products. So, one thing about a dot product is I'm going to write this in blue. So, another thing about the dot product is A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle theta. Well, if we actually wrote the A vector as A is equal to AX I hat plus A sub Y J hat plus A sub Z K hat, where AX is the X component, AY is the Y component, and AZ is the Z component, then we can do a dot product. And another way that actually might save you some time to write it is you could also write this vector. In this case, it's the B vector instead of the A vector. But in this case, you just write it BX, comma, BY, comma, BZ. But notice I'm putting it in a less than and greater than symbol. In other words, instead of using parentheses like we do for points, we use less than and greater than symbols, and that represents the components of a vector. So the b sub x is the x component, the b sub y is the y component, and the b sub z is the z component. So that's just two really easy ways to indicate that. Now, we might also argue, because it turns out this is right, it turns out that vectors and numbers in general form what we call an algebra. You're not used to using algebra in that sense, I'm sure. But if you take, let's say, linear algebra, that's going to be the first place where you run into the idea of an algebra. So those rules that you learned about in pre-algebra and then in algebra 1, and you use them, for instance, to solve equations like a plus B is equal to B plus A, or A times B is equal to B times A, or A times parenthesis C plus D, close parenthesis, is equal to A times C plus A times D. That's the distributive property. And all those other properties that you remember, in addition to the commutative property of addition and multiplication and the distributive property, all of those things are true. And if you have them, they form what's called an algebra. And one of the existing algebras in nature is a vector algebra. Another one is matrix algebra. Another one's just plain arithmetic algebra. There's another one called Lie algebra, which can be represented as a matrix algebra, but it can also be represented by other things. So the reason why I'm telling you all that is it's not unreasonable for us to expect that the dot product is going to obey a distributive property. So I'm going to write the dot product, instead of just writing it as AB cosine theta, I'm going to write it as AX I hat plus AY J hat plus AZ K hat dotted with, notice I formally write that in parentheses and put a dot there. And now I'm going to write BX I hat plus BY J hat plus BZ K hat. And what this tells us, by you knowing the concept of an algebra is a bigger thing, you now say, oh, well, it does not seem unreasonable for me to expect the distributive property applies to dot products of vectors. And it does. That's a fundamental idea in science and vectors and math and all that good stuff. So the distributive property says you take the first term and multiply it by the first term. Then you multiply it by the second term, and then you multiply it by the third term. And of course, you're adding those up. So you get ax I hat dotted with bx I hat plus ax I hat dotted with byj hat plus ax I hat dotted with bzk hat. That's just the first of the distributive properties. Then we do the same thing, only this time we do it with the second term. So it'll be AYJ hat dotted with BXI hat, and then you do AYJ hat dotted with BYJ hat, and then you do AYJ hat dotted with BZK hat. And then finally, you're going to do it with the third term, and that's going to happen the same way, like that. So you should ultimately get 3 times 3 or 9 terms. With that in mind, I can write those out as follows. And believe it or not, this is actually going to give you a nice formula that makes some sense to you because you're seeing it happen in real time. So when the AXI hat hits the BXI hat, you get AXI hat dotted with BXI hat plus AXI hat dotted with BY J hat plus A X I hat dotted with B Z K hat plus A Y J hat dotted with B X I hat plus A Y J hat dotted with B Y J hat plus A Y J hat dotted with B Z K hat plus, now I got to do the third term, that's A Z K hat dotted with B X I hat plus A Z K hat dotted with B Y J hat plus A Z K hat dotted with B Z K hat. Okay. Now, before I make this any simpler, I want to use my original definition of the dot product as AB cosine theta to work out something. So, for instance, I hat dot I hat, according to our definition, A dot B is equal to A times B times the cosine of the angle between them. So, can anybody tell me what the magnitude of the I hat vector is? It has a hat on it, so that's a big indicator. Anybody tell me the magnitude of the I hat vector? Type it in the comments if you don't want to speak up. So, vectors with hats on them in the physics and engineering world generally are considered to be what we call unit vectors. So, their magnitude is 1 unit. So, when I go to apply the formula, A dot B is equal to AB cosine theta, then the A for the I hat dot I hat is 1, and the B for the I hat dot I hat is also 1. So this becomes 1 times 1. Now, I hat and I hat, if we put them tail to tail, what would be the angle between those two vectors? Anybody?
Is it 90?
Not with I hat dot I hat. But with I hat dot J hat or I hat dot K hat or any of those other ones that are different, then yes, it's 90.
So
But when
would
the
it be
two
zero?
vectors are identical, what is it, Michelle?
Would it be zero?
Exactly. So it's 1 times 1 times the cosine of 0. Does anybody recall what the cosine of 0 is?
1.
Exactly. So I hat dot I hat is just 1. Now watch this. if I do I hat dot j hat, and by the way, the answer here for I hat dot j hat is going to be the same as the answer for I hat dot k hat, as well as the answer for j hat dot k hat. So the magnitude of I is again 1. Since j hat also has a hat on it, its magnitude is also 1. But as Michelle said, in this case, the angle between them is 90 degrees. And of course, the cosine of 90 is 0. So that means I hat dot j hat is 0, I hat dot k hat is 0, and j hat dot k hat is also 0. And not only that, you can see since a dot b is equal to a times b times the cosine of the angle between them, changing the order doesn't matter at all. So when I say I hat dot j hat equals 0, that means j hat dot I hat is also 0. That means I hat dot j hat, I hat dot k hat being 0 also means that k hat dot I hat is 0. And j hat dot k hat equals 0 tells us that k hat dot j hat is also 0. So that's a really important thing to make sense of, and we're going to use that over and over and over again. Not only that, that gives us yet another formula to calculate the dot product. So I've already given you a times b times the cosine of the angle between them, but now I can simplify this. It turns out that the dot product, just like the cross product, which I haven't shown you yet either, that's also called the vector product, but just like that, it's what we call a linear operation. So in this context, what a linear operation means is that when I have, for instance, ax I hat dot bx I hat, as I have right here, okay, this ax and this bx are just scalars. I can pull them out from the dot product and then just let the dot product act on I hat and I hat. So that's the beauty of a linear operator. You can pull those scalar quantities out in front and just leave the dot product out by itself where it's just acting on vectors. So that first line is now going to become AX BX I hat dot I hat, like that. And of course, we've already figured out that I hat dot I hat is 1. The other one, the next term is ax I hat dot by j hat. Since it's linear, that means I can bring the ax out in front and the by out in front, and then I have left I hat dot j hat. But we already worked out that I hat dot j hat is 0. So you should be able to see from that alone that this is going to be 0. This is going to be 0. This is going to be 0. That is going to be 0. That is going to be 0. That is going to be 0. And all we have left is basically plus. I did AX BX and I did AX BY. Now I have AX BZ, that's 0. I also have AY BX, that's 0. I also have AY BY, but that one gives me 1, so that's AY BY times J hat dot J hat, which is 1. And now I have AY BZ, which gives me 0. And then I have AZBX, which gives me 0. And then I have AZBY, which gives me 0. And finally, all I have is AZBZ K hat dot K hat, which is 1. So finally, I now have a new result. That new result is AX times BX plus AY times BY plus AZ times BZ. So our formula for the dot product just got a little more complete because now we know that the dot product or the scalar product is not only A times B times the cosine of the angle between them, it's also AX BX plus AY BY plus AZ BZ. That is the entirety of the dot product formula. Okay. Now, I will tell you that the exact same thing can be done with the cross product. So, for instance, the cross product is written like this: A vector cross with B vector. And just like the dot product, it has a simple formula for its magnitude, but this actually spits out a vector quantity. Okay, the cross product, which is also called the vector product, takes two vectors and spits out another vector. But the neat thing is, if we just want to compute the magnitude of this vector, we can put the absolute value bars around it. And when you do that, it turns out the formula is just A times B times the sine of the angle between them. So I think you can see that this will, in fact, since cosine theta gave us the parallel component, clearly sine theta would give us the perpendicular component. So this one is called the vector product, and it's also called the cross product. And it gives you the perpendicular components. A perpendicular to B, or B perpendicular to A. So that's a key thing to understand. Anybody have any questions on that? All right. With that in mind, let's take a very simple triangle, or let's take a couple simple vectors. I'm going to go ahead and draw a coordinate system just to make it nice and simple. Here's my x-axis. Here's my y-axis. Let's say I have a vector that goes from the origin 3 units to the right while moving 4 units up. Y'all probably can guess exactly what that vector is and what that angle is even. But just in case, I'm going to draw it like this. So let's call this vector A. And notice it has 3 units to the right and 4 units up. Okay. So this is obviously what we'd call the 3, 4, 5 triangle. And we could write that vector A as 3 I hat plus 4 j hat, which also happens to be A is equal to 5 units at, in this case, we would actually take the inverse tangent of 4 over 3. So if I take tangent inverse 4, well, let me put that in parentheses. 4 divided by 3, close parentheses, you get 51.1, or excuse me, 53.13. So it'd be at 53.13 degrees. That's another way we could express the vector A. Anybody have any questions about that or objections or anything? All right, so let's say vector B is going to be a vector that points just to the right, and it is going to have a magnitude of 5, so that the B vector is 5 I hat. Okay? Now that we have that, let's calculate what A dot B is, because I need you guys to understand what it looks like. I can't tell you how many times I give a test or a final exam and I ask students to calculate a dot product, and they'll say, 7 J hat or 4 K hat or something crazy like that. There's no vectors. When you take a dot product, it only spits out a scalar, so there shouldn't be any I hats or J hats. So I want to make sure y'all know how to do that, and here's how we're going to do it. What is A dot B? That's the question. So we know A dot B is equal to, remember I said AX BX plus AY BY plus AZ BZ? So, can anybody tell me what the x component of vector A is?
3,
3,
3. Yep. And what's the x component of vector B?
5,
Very good. And notice I just put a plus next. I don't put a I hat, I don't put a J hat, I just put a plus. Now, what's the y component of A?
4,
Exactly. And what is the y component of B? So
0.
little bit of a trick question. Yes, it's 0. And of course, from that, you can now figure out that the z components for both of them are 0. So in fact, A dot B is just 15. Now, if these two vectors were newtons, that'd be 15 newtons squared. If they were meters, it'd be 15 meters squared. But I'm just treating them as pure numerical vectors, so we don't have any units. But I've now figured out that. Now, this angle right here, actually, let me do it this way. This angle right here is something we would like to figure out. I know what it's got to be because I just finished showing you that the 345 triangle has an angle of 53.13 degrees between it and the between it and the x-axis. So we expect that answer to be 53.13 degrees. What I'm going to do is show you how you can compute it, and this will be used all the time. For instance, there's a course called solid state physics, and in that you constantly will draw a vector from one atom in a lattice to another atom in a lattice. So, for instance, there's body centered cubic, which is sort of like atom, 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 atom. That's the square. And then atom, 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 atom. That's another square projected out in front of it. And then dead center in the middle, literally in the volumetric center of that cube is a single vector or a single atom as well. So you could draw a vector from this front right corner to that middle one. That's one vector. And then you could draw a vector from this front right corner to that front left corner. That's another vector. And it turns out in studying those lattices and understanding how materials behave, it's important to understand the angle between the two bonds, the bond that bonds that corner atom to the center and the bond that bonds that corner atom to the other corner. It's important to know what that angle is, and we do that by this dot product. So now what we know is A dot B is also equal to, and so here is what is the angle between A and B. So in this case, we're going to use A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. We already know what A dot B is, so we can automatically write 15 is equal to. Now, can anybody tell me the magnitude of vector A?
5,
Exactly. And what about the magnitude of vector B? Exactly, Will. Yeah, that one's 5 as well. So now I've got 15 equals 5 times the cosine of the angle between them. That means the angle between them, theta, should be equal to the inverse cosine of 15 over 25 because 5 times 5 is 25. If I take the inverse cosine, so I'm doing shift cosine of 15 divided by 25, which obviously is 3/5. If I take that, I get 53.13 degrees. So that's how you can use the dot product to find the angle between two vectors, for instance. So I actually did two examples here. I did example 1, and then I did example 2. So example 1 was just computing a dot product. Example 2 was, and I don't know why I wrote a 1 there. Example two was once you know the dot product, can you tell me the angle between two vectors? So we've now done two examples on dot products. Hopefully that's helping you. Does anybody have any questions
Is
regarding this dot product or anything?
is there a way to like, I guess, say what a question like that looks like in a word problem?
Yeah, it could literally be, and you'll see this when you start taking the practice test, which I'm going to open up after class tonight. There's a face-to-face, I mean, an online test that's due tonight, and that practice test is still available, but it's going to disappear at 11:59. I'm going to open up the other one, which is for the next. Not only face-to-face test, but also for the next online test. That'll be opened up and it'll have problems in there. But a typical problem would be like, consider the vector 3 I hat plus 4 j hat and the other vector b equals 5 I hat. Calculate the dot product. Part B, calculate the angle between them. That's how I would literally word this question. And you'll see there'll be questions worded just like that. Usually they're only one part because we made them up as multiple choice problems. And what we'll do is make two separate questions. We'll have one question where you're asked to compute the dot product, then another question where you're asked to use the dot product to compute the angle between them. But that would be a typical one. Does that make sense, Michelle?
Yeah, thank you.
No problem. Now, to see another one, I'm going to allow you guys to think in terms of, oops, I'm in the wrong class with that one. I'm going to allow you guys to think in terms of one of the examples in the book. So I'm opening that up right now. I thought I had it open already, but I did not. So I'm going to chapter 7, which is problematic because the last class I was working in was not anywhere near chapter 7. They're way out at page 600 or something. So I'm going to go to, let's say, page 200 and see what happens there. That's a little further than I wanted. That jumped me into chapter 8, but that's closer than I expected, so I'm not too upset with that. So work done by a constant force is where we're at. So I'm going to do example 7.1, and I'll read that to you. So example, oops. Example 7.1 says a person pulls a 50-kilogram crate 40 meters along a horizontal floor by a constant force of Fp equals 100 newtons, which acts at 37-degree angle as shown in figure 7.3. The floor is rough and exerts a friction force of F friction equals 50 newtons. Determine A, the work done by each force acting on the crate, and B, the net work done on the crate. Okay, so I'm going to go ahead and draw the diagram so we can make use of that. Here's the crate that we're talking about. And what we have acting on it is this will be a level surface right here. So it's all level. And what I'm going to do is I'm going to put a little swath in there like that, and this will be a cutout because obviously I don't want to draw something a whole 40 meters long. So what I'm going to do is say, okay, well, this distance from here to here is 40 meters. Okay, so that's the distance I'm actually traveling. Now, the forces acting on it are the weight W, which equals mg, which equals 490 newtons. There's also a normal force, F normal. Now, in addition to that, there is a force that's not basically has not been uh, translated into components parallel to the x or y axes. So I'm just going to draw it a random color black, and that's going to be Fp, whose magnitude is 100 newtons. Now, the angle between it and the displacement vector, that angle theta is 37 degrees, and that's them trying to make sure you're thinking of this as if it's a 3, 4, 5 triangle. Now, in addition to that, we have one more force acting on it, and that force acts in the negative x direction. So I drew it blue like negative, and that force I'm calling just script F, and that's 50 newtons. I'm assuming all these things have at least 2 sig figs. So the 100 newtons is 3 sig figs, the 490 is 3 sig figs, but the 50 is 2 sig figs. And what they want us to do is A, work equals question mark for each force. And B, they want to know the net work done. W net equals question mark. So solution work right now, since it's a constant force, constant direction, all over the constant displacement vector D, that work is just F dotted with the displacement vector. And we also know that A dot B is equal to A times B times the cosine of the angle between them. So that's what we're using here. I'm going to start off with part A. I'm going to say, what is, well, for starters, can anybody tell me what you think the normal force will be? Ooh, actually, it's a little errant to call that the normal force. I've been treating it like it was the normal force, but it's not technically.
490.
Yeah, it should be very close to 490. The problem is once I break that FP up into forces, that's going to decrease the normal force to a little bit less than 490. So I should take that into account. By doing that, what I'm going to do is I'm going to say this part right here is FP parallel, and that's going to be 100 newtons times the cosine of 37. 100 cosine 37 gives me about 80. Oops. So this parallel one will be about 80 newtons. And then it also has this perpendicular component. FP perpendicular is going to be 100 times the sine of 37. And that gives me about 60 newtons. Okay. Now, the summation of the forces in the y direction equals mass times acceleration in the y direction. We're actually sliding this along that horizontal floor. So the y is going to be 0, and then it's still 0, and then it's still 0. So that means the acceleration in the y direction is 0. And what we're going to get is, in fact, F normal, which points up, plus 60 newtons, which points up, minus 490 newtons is equal to 0. So that tells us the normal force is actually equal to 490 minus 60, which would be 430 newtons. Okay. Now, I did this, for instance, in class today, and I completely neglected to remember that the FP has a vertical component, so I just treated it like the normal force was just 490. That is wrong. That's not really correct to do it, but I wanted to show you that this is what you have to do. Now that we have that, I can say uh, I want to calculate the work done by FP. So the work done by FP is equal to the dot product of FP and the D vector. The D vector is just, let's write that here, D equals 40 meters in the I hat direction. So that's really what the D vector is. And we could say the force vector, FP, is actually equal to 80 newtons I hat plus 60 newtons J hat. So obviously you can see that the net result is that magnitude is 100 newtons. So the force is going to be 100 newtons. That's the magnitude according to the dot product. And then the magnitude of the second vector is 40 meters. And then the cosine of the angle between them, you see the angle between the D vector and the actual FP vector is in fact 37 degrees. So this gives us 100 times 40 times cosine 37, and that gives me essentially 3,200 newtons. If I were to round that to two sig figs, it would come out to 3,200. In fact, it's 3,196 newtons. But that's what it truly would be. So if I'm using that calculation, if I'm using that number later, it would be better for me to use 3,196 so that carry a couple extra sig figs. But and that's Newton meter, by the way. It's a Newton times a meter. Now, I should point out to you that that is a new unit. We've seen that work is force times distance, and force has units of newtons, and distance has units of meters. So work has units of newtons times meters, and it turns out that 1 Newton meter is defined to be 1 joule. That is the same joule that you're used to if you've had chemistry or something like that. But the main thing I'm telling you about that is because that's a unit that we're going to continue to use here on out. So we now know that the unit is actually the joule, and we'd say the work done by the pulling force is 30 or 3,196 joules. So I'm going to circle that as part of the answer for part A. Now, I also have work done by the normal force. So the work done by F normal is equal to, as the dot product tells us, it's the magnitude of the normal force, which we found was 430 newtons, times the magnitude of the displacement vector, which is 40 meters, times the cosine of the angle between them. Well, the angle between the normal force Fn and the displacement vector, which is completely horizontal, is 90 degrees. So the cosine of 90, hopefully you guys remember, is in fact 0. So the work done by the normal force is 0 joules. So the work done by the normal force is 0 joules. Now we also want the work done by the weight. So the work done by the weight is equal to the magnitude of the weight, that's 490 newtons, times the magnitude of the displacement, which is 40 meters, times the cosine of the angle between them. In this case, the angle between them is technically negative 90, but the cosine of negative 90 is the same as the cosine of 90, and that both happens to be equal to 0. So the work done by the weight is 0 joules. So we now have the work done by the weight is 0. Now all we have left is the work done by the friction, and I call that just plain F instead of the version that your book uses. So the magnitude of the force, the vector force that represents friction, is just 50 newtons. The displacement vector is still 40 meters, and the angle between them you might think is 0 because they're parallel, but technically they're anti-parallel. D goes to the right and friction goes to the left, so the angle between them is actually 180, and that's really important because it's going to teach us something very specific about work. And of course, the cosine of 180 is -1, so I'm going to get -2,000 joules is equal to the work done by friction. Now, that is perfectly normal. In fact, I want you guys to remember that if the displacement is one direction and there's no component of the force that's exactly parallel to that, but there is one that's anti-parallel to that, then that means that work should come out negative. So if a force has a component that's this way and the displacement is that way, you should expect the work to come out to be negative. Any questions on that? Okay. So now for part B, we're asked what is the net work done. So W net is equal to W1 plus W2 plus dot 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 for however many forces acting on it. In this case, it's four. So in this case, it's going to be 3,196 joules plus 0 joules plus 0 joules. And work is a scalar quantity, so we're not having to do vectors here. And then minus, it's technically plus a negative 2,000 joules. And of course, that gives us 1,196 is the net work done. So W net is equal to 1,196 joules, and that's the total answer. Anybody have any questions on that? All right. So now I've talked about work being a scalar quantity. I've talked about a dot product. I showed you how to do a dot product. I showed you how to use a dot product to find the angle between two vectors. All that stuff is valuable and all that stuff is stuff we need. But I'm going to go ahead and derive another expression so you can start getting the lion's share of the homework done. And this is what we call the work energy theorem. So I'm going to do a quick and dirty derivation of that work energy theorem so you'll have the result to be able to work with. And then I'm going to show you an actual kind of a rougher version of calculating work when the force does vary. So I'll have to do that as well. So first off, work energy theorem. So the last problem asked us about W net. And that's what the work energy theorem is supposed to be about. It's the total work done. If you take Newton's second law, and remember that's something that I warned you guys in class that hey, if you have a whole subsection of your textbook or a chapter of your textbook that's called blah 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 law, then you better commit that blah 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 law to memory. Not only that one, but specifically which ones are which. So, for instance, when I say Newton's first law, you better tell me which one's Newton's first law, which one's Newton's second law, which one's Newton's third law. In addition to knowing all three, you also have to know which ones are which. So Newton's second law says the summation of the forces is equal to mass times acceleration. And usually, or at least so far, most of our accelerations have been a constant. If they're not a constant, then you can't actually call that A. You have to call that dv dt, the derivative of velocity with respect to time, or d2r over dt squared, the derivative of the position, the second order derivative of the position with respect to time. So I'm going to go a little further and say this is m dv dt. Okay. Now, this right here, this summation of the forces, the whole reason I put that sigma on there is because I want you guys to remember that it's not a particular force that goes on the the left hand side of Newton's second law. It's F net. It's the sum of all the external forces. So work net should equal the actual generalization of work. So I mentioned to you what that would be. Here's where I'm going to go ahead and tell you that. Let me erase this because I got ahead of myself by writing W net. The formula for work, the general formula for work is equal to the integral of F dot dl. That's the general formula in case the actual force varies along the displacement vector. And sometimes the displacement vector, remember, that's just a straight line that points from where you started to where you ended up. The path actually might be curved and all sorts of stuff. So you have to actually divvy that up. With that in mind, I should tell you that this goes on the assumption that F is what we call a vector field. So what I mean by a field is it takes a value of x, a value of y, a value of z, which obviously, if you have a x, y, and z, that indicates a particular point in space. So each of these components could be functions of x, y, and z. They might even be functions of the velocity in the x direction, the velocity in the y direction, the velocity in the z direction, and they could be functions of time as well. The main thing is just to remember that they are functions, and it's a function that gives you the scalar part of the component. So in this case, I'd say f is equal to f sub x I hat plus f sub y j hat plus f sub z k hat. And I just want to remind you that those fx's, fy's, and fz's could be functions of x, y, z, v sub x, v sub y, v sub z, and time. Additionally, the dl, generically speaking, is dx I hat plus dy j hat plus dz k hat. So that's really what the actual vector formula for the work is when the force actually varies along the path. You have to use the F expressed here and the DL as expressed there, and I'll show you how to do that in a second. Yes, Michelle?
What does the DL stand for again?
It's a differential line element, so it's infinitesimally long, and it's basically a what we call a tangent vector to some part of the path. So, like if the path is y equals x squared, you would come and put a little dot somewhere on that graph y equals x squared, and you draw a little tangent vector that's infinitesimally long. That would be the DL vector.
Okay, thank you.
No problem. And we'll get to that in a second. Like I said, I just needed this formula. So now that I have that, I can go ahead and calculate W net, which according to this should be the integral of F net dotted with DL. And as I said, the summation of the forces that I put over there is the F net. So I can continue on by replacing F net with the integral of the summation of the forces dotted with dl like that. But now, in place of the summation of forces, I'm going to put in the right hand side of Newton's second law. So that's going to be m dv dt dotted with dl. Okay. Now, you guys probably know from your adventures in calculus that dvdt or dxdt, that's like a symbol that you use to represent a derivative, right? Well, it turns out that it's not just a symbol, it's also a formula in some sense. So when I write dx over dt, that is the derivative of x with respect to time, but dx by itself in the numerator is a quantity, and dt down in the bottom in the denominator, that is a quantity as well. In fact, we generally call them what you call one forms. So if you took a much more advanced calculus 3, sometimes they'll just call that a course on differential forms. Or you could later on, if you're at a bigger university, you can take a differential forms class and they'd learn what that is. The only reason why I'm telling you all this is because I'm getting ready to use the dv and the dl and the dt in a way that you're not familiar with, but it's completely sanctioned because those things are quantities and you can do this with them. So with that in mind, we also know, as I told you before, A dot B is B dot A, so it's perfectly fine to change the order. If you get to quantum mechanics, that's a little different, but other than that, A dot B is the same as B dot A. So with that in mind, I'm going to replace not the whole vector dv/dt and dl. I'm just going to take the top part dv and trade that with the dl, and I'm going to put the dv where the dl was, and I'm going to put the dl where the dv is. I'm also going to pull that mass out in front because that's a constant, so it's going to get the integral of dl dt dotted with dv. Now, it might help you to think of the units, but now that you have dLdt, what do you think that quantity is? And again, think about the units that might help you. Can anybody tell me what dLdt would represent?
Is it acceleration?
Close. One step down further. So you took two derivatives instead of one.
Okay. Hmm.
So what's one step less than the second derivative? It's actually
Is it
velocity. Okay. So the dl, which we learned was a differential length element, so that has units of meters, and the dt has units of time, so it's meters per second. And dl dt in meters per second should tell you, oh, that's velocity. So I now ought to have is the integral of v dot dv, which now that dv is represents a tangent vector, that means dv and v are parallel. So the dot product just becomes v times dv. So now I've got m times the integral of v dv. And can anybody tell me what the integral of v dv is?
V squared over 2.
Exactly. And we're going to integrate it from the initial to the final. So that's why I just put that there. So what we get is 1/2. The m is already there. And then I'm going to get v squared. And then I have to evaluate it at the initial position and the final position, or the initial velocity and the final velocity. So I end up getting 1/2 mv final squared minus 1/2 mv initial squared. That quantity became so important. In fact, Madame de Châtelet, who was the first person to write a translation of Newton's Principia, she translated it from the Latin to French at the ripe old age of, I think, 16. She was quite the beast when it comes to being mathematically and physically skilled. She actually had Voltaire, if in case y'all are familiar with Voltaire, that he was sort of her boy toy. So you can imagine, this 17, 18-year old who, treated this older man like a little toy for herself to play with. She had to be brilliant because Voltaire is, quite brilliant himself. But that's who she is. And she, in fact, named this quantity the oomph, which is so French. I mean, it's just oomph. But anyways, kinetic energy is defined to be 1/2 mass times velocity squared. So what we just found was W net, the total work done, is equal to the change in kinetic energy. And whenever you see that triangle written with the little point up at the top, that means final minus initial. So that means K final minus K initial is W net, and that's the work energy theorem. Now, that can be used, for instance, to determine in terms of car wrecks. If you've ever seen a car wreck, sometimes you'll see police officers out with a little trundle wheel, and they're walking the skid marks of the wreck. And what they're doing is measuring how long the skid marks are. And basically, if you calculate the work done by friction, it's the friction force times the distance, because the friction force is anti-parallel to the displacement vector. So you're automatically just going to get F times D, and that'll give you the friction force. Well, the friction force, if you take that and multiply it by the length, that'll give you the work done by friction. And that work done has to be the change in kinetic energy. And the final kinetic energy obviously is zero. So you can now figure out what the initial kinetic energy is. You can look up the mass of the car. You can look up well, once you have that mass of the car, then you can use the fact that that's m in 1/2 mv squared, and you can solve for the v that the person had just before they skidded on the brakes, so you can tell whether or not they were speeding during the wreck. So that's one of the common ways we can use the work energy theorem. I'm going to do some more examples of this after the break, but I wanted to show you the work energy theorem so you can start doing homeworks on it. And now I'm going to show you how to work that line integral slash path integral that I was just talking about. So now that I've covered this, I'm going to do a work problem using using the path integral. So what is the work done in moving from xy equals 0, 0 to 2 comma 4 along the path y equals x squared. And if f is equal to 2xy I hat plus x squared, or excuse me, plus y squared j hat. Okay, so if we actually drew this, just to let you know what it would look like, it would start here. That's the initial point, and this is 1, this is 2, this is 1, 2, 3, 4. There's y, and the path we're taking is that one right here, and that's y equals x squared. We know that dl is supposed to equal dx I hat. This is only two-dimensional, so I'm only going to write two of the components here. So plus dy j hat. Now, when you're actually doing an integral like work equals the integral of f dot dl, I said that's a path or a line integral. And what makes it a path or a line integral is you've got to evaluate the integrand, which in this case is f dot dl, on the line y equals x squared, or whatever line you're choosing. So everywhere I see y, I need to replace that with x squared. And not only that, if I see dy, y equals x squared implies dy is 2x dx. So that means I should also replace dy with 2x dx. So now I can say this is the integral from 0, 0 to 2, 4 of 2xy I hat plus y squared j hat. That's going to be dotted with dx I hat plus dy j hat, which is going to be equal to, now I'm going to do my dot product, and we get 2xy dx times I hat dot I hat, which we know is 1, plus y squared dy times j hat dot j hat, which we also know is 1. So, and this is from 0, 0 to 2, 4. We're going to settle that a little bit in a little bit. Now I've got to replace the y with x squared. So this is going to become the integral from 0, 0 to 2, 4 of 2x cubed, because y has been replaced with x squared, dx plus x to the fourth, and then the dy is going to become 2x dx. So actually, let me do this. And if you guys got a split, that's okay. I know I'm getting close to running over. I'll finish this problem up, and I'll also wait for you guys for the last one to leave. But if you need to leave, go ahead. It's not a big deal. The other part of the integral is going to be y squared, which I'm going to replace with x, what each y with x squared. So that's going to be x to the fourth. So I'm going to say x to the fourth, and then the dy becomes 2x dx, like that. And again, this is from 0, 0 to 2, 4. Now you can see everything's integrating in terms of x. So I only have to integrate from x equals 0 to x equals 2. So it's going to be the integral from 0 to 2 of 2x cubed dx plus the integral from 0 to 2 of 2x to the fifth dx. And this is going to be, when I integrate 2x cubed, I'm going to get 2/6 x, or excuse me, 2/4 x to the fourth. And of course, 2/4 is 1/2. So that's 1/2 x to the fourth from 0 to 2. Plus, in this case, I'm going to integrate 2x to the fifth. That's going to be 2/6 x to the sixth. And of course, 2/6 is 1/3. So this will be 1/3 x to the sixth. And that's going to be from 0 to 2. 2 to the fourth is 16. So this is going to be 8 Newton meters. And then x to the sixth is 64 because x to the fifth is 32, x to the sixth is 64. So this will be 64 over 3 Newton meters. And obviously that's going to be 24 over 3 plus 64 over 3, which would be 88 over 3 joules. And that's the total work done in integrating along that path. So that's how you can compute a a path integral. Okay. If you find it in your calculus text, they generally use parametric equations. So we don't do that in physics usually. I mean, we can. We just normally just think of it as y equals x squared and stuff like that. So this is me showing you how I do it in the physics world. But you can also look up how you do it with parameterization. So for instance, the equation y equals x squared, you're going to make x into t, and then you're going to make y into t squared, and you're going to make z into 0. And that's your parametric equation, and then you work it out that way. But that's it. I will work more examples next time we're done. You guys are free to go. Remember to chat me your first and last name. Don't forget to do your online test tonight, and don't forget to email me if you've missed online test 1 or online test 2 because you got to get them done over the break. When we get back from the break, you will have a face-to-face test that'll be due that week. Normally what I do is I'll make it due not the Monday return from break, but the Monday thereafter. It'll have to be done by that day. So I'll send out times that I'll be tutoring, that I'll be doing the proctoring, as well as the other normal stuff. So have a good one, everybody. I hope you have a wonderful break. Thanks for coming. Let me know if I can do anything for you, and I'll wait for the last person to leave in case you have any questions.